The cosmos is a cathedral of unanswered questions. We gaze up at a night sky filled with stars, yet what we see is just the faintest glimmer of a reality so strange it defies our basic intuition. This is a universe dominated by forces we cannot see, dotted with signals we cannot explain, and expanding toward a fate we cannot predict. From the ghostly pull of dark matter shaping galaxies to the eerie silence that greets our search for other minds, we are surrounded by profound cosmic mysteries. By the end of this journey, you will stand at the very frontier of human knowledge, looking out at the 25 greatest puzzles that define our reality. We will confront the energy that is tearing space apart, decipher a one-time signal that screamed from the void, and question why we are here at all when physics says we should not be. What aspect of the unknown universe fills you with the most wonder? Perhaps the most unsettling discovery in modern cosmology is that the universe is not just expanding, it is running away from us. For decades, astronomers believed the gravitational pull of all the matter in the cosmos would eventually slow the great outward rush that began with the Big Bang. It was a logical assumption. Then, in the late 1990s, two independent teams of researchers made a shocking observation. By studying distant exploding stars called supernovae, they measured the expansion rate of the universe across vast stretches of time. They expected to see the expansion slowing down. Instead, they found it was speeding up. Something was pushing galaxies apart faster and faster, a repulsive force woven into the fabric of space itself. We call this something dark energy, and it is the dominant player in our cosmic story. Think of the entire energy budget of the universe as a pie. All the stars, planets, gas clouds, and every single atom you have ever seen or touched, all the normal matter, makes up less than 5% of that pie. The mysterious dark matter we discussed earlier accounts for about 27%. The remaining 68%, the overwhelming majority of everything that exists, is dark energy. It is the silent, invisible engine of cosmic acceleration. But what is it? The leading idea comes from Albert Einstein himself, though he initially considered it his greatest blunder. He introduced a fudge factor into his equations called the cosmological constant, a fixed energy density inherent to empty space. This vacuum energy could produce the repulsive push we see. The problem is, when physicists try to calculate how strong this vacuum energy should be using quantum theory, their answer is wrong by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the history of science. The alternative is a dynamic field called quintessence, a kind of fifth force that changes over time. But quintessence, too, has no direct evidence and introduces its own set of puzzles. This is the heart of the mystery. We have measured the effect of dark energy with high precision, yet its fundamental nature remains utterly unknown. Its behavior holds the key to our ultimate fate. If dark energy remains constant, as the cosmological constant suggests, the acceleration will continue forever. In a distant future, all galaxies beyond our local group will vanish over the cosmic horizon, leaving our descendants in an island universe surrounded by an endless, empty dark. If dark energy grows stronger, it could eventually tear apart galaxies, stars, planets, and even atoms themselves in a catastrophic big rip. The fate of every structure in the cosmos, from the grandest galaxy cluster to the smallest living cell, hinges on the identity of this phantom force we cannot see, touch, or currently understand. While dark energy dictates the future of space itself, another unseen hand has already sculpted the universe we see today. Look at any grand spiral galaxy, its arms gracefully sweeping through the void. According to the laws of gravity, the stars on the outer edges of those arms should orbit the galactic center much more slowly than the stars near the core, just as Pluto takes far longer to orbit the Sun than Mercury does. But when astronomers measured these rotation speeds in the 1970s, they found something impossible. The stars on the outskirts were whipping around just as fast as those near the center. It was as if the entire galaxy was embedded in a giant, invisible sphere of mass, a halo of something providing extra gravitational glue to hold it all together. This was our first major clue to dark matter. The evidence only grew stronger. We see its signature in the way massive clusters of galaxies bend light from objects behind them, a phenomenon called gravitational lensing. The amount of bending is so extreme that it requires far more mass than all the visible stars and gas in those clusters combined. We even see its influence in the very first patterns of light in the universe, the cosmic microwave background. The conclusion is inescapable. For every ounce of normal matter that makes up stars, planets, and us, there is about 5 times more dark matter. It is the hidden skeleton of the cosmos, the framework upon which galaxies are built. So what is it? We know what it is not. It is not planets, black holes, or cold gas. Those are made of normal atoms, and we have accounted for them. Dark matter does not interact with light at all. It does not shine, it does not glow, it does not cast a shadow. It passes through normal matter like a ghost walking through a wall. This means it must be something entirely new, a fundamental particle not found in our standard model of physics. The leading candidate for decades has been the WIMP, the weakly interacting massive particle. As the name suggests, these hypothetical particles would have mass and interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. Teams of scientists have built exquisitely sensitive experiments deep underground, in old mines and beneath mountains to shield them from cosmic rays. They wait in profound silence, hoping to hear the faintest tick of a WIMP bumping into an atomic nucleus. So far, the detectors have heard nothing. Another intriguing possibility is the action, a particle so lightweight and numerous it could behave like a strange, invisible fluid permeating all of space. New experiments are using powerful magnetic fields to try and convert these phantom actions into detectable photons. The hunt is global, from deep underground laboratories to telescopes scanning the heavens for indirect signals of dark matter particles annihilating each other. This is the profound irony of our cosmic situation. We can map the distribution of dark matter across the universe with stunning precision by watching how its gravity tugs on the light of distant galaxies. We know it is essential, the architect of cosmic structure. Yet after decades of searching, we still do not know what it is made of. It is the most familiar stranger in the universe, a presence we feel in the motion of every galaxy but cannot touch or see. That ghostly dark matter halo is not the only reason our universe should be empty. There is a deeper, more fundamental puzzle woven into the laws of physics themselves, a mystery that asks why you, the Earth, and the stars exist at all. According to our best theories, the Big Bang should have created a perfectly symmetrical universe. For every particle of matter, a corresponding particle of antimatter should have been born. Think of antimatter as matter's perfect, malevolent twin. It has the same mass but opposite charge. When a particle meets its antimatter counterpart, they do not simply cancel out. They annihilate each other in a flash of pure energy, vanishing completely. In a perfectly balanced cosmic birth, all the matter and all the antimatter should have found each other immediately after the Big Bang. They would have mutually destroyed themselves, leaving behind a vast, lifeless sea of radiation. Nothing made of atoms should have remained, and yet here we are. The fact that you are listening to this is direct, irrefutable proof that the symmetry was broken. Somehow, for every 1 billion antimatter particles created in the early universe, there were 1,000,000,001 matter particles. That 1 in a billion imbalance is all that survived the Great Annihilation. Every galaxy, every planet, every living thing is made from the ashes of that 1 part in a billion surplus. So what tipped the scales? Physicists call the necessary break in symmetry CP violation. It means the laws of physics treat particles and their antiparticles slightly differently, giving matter a tiny, built-in advantage. We have observed this effect in certain exotic particles like kaons and B-mesons in particle accelerators. The problem is, the amount of CP violation we have measured is far, far too small. It is a faint whisper when we need a cosmic shout. It accounts for only a minuscule fraction of the imbalance needed to build our material universe. This means there must be a much stronger source of symmetry breaking out there, a fundamental law we have not yet discovered. The search for this new physics is a quest to explain our own existence. At facilities like CERN, scientists are smashing particles together at nearly the speed of light, meticulously comparing the behavior of matter and antimatter with unimaginable precision. They are hunting for any slight difference in how they decay, how they oscillate, any clue that would reveal nature's hidden bias toward creation. Some theories suggest the answer lies with neutrinos, those ghostly particles that barely interact with anything. If neutrinos are their own antiparticles, a special type known as Majorana particles, they could have triggered processes in the searing heat of the early cosmos that favored matter. Others look to conditions present only in the first fractions of a second after the Big Bang, where extreme energies may have unlocked forces we can no longer see. This is not an abstract puzzle, it is the ultimate origin story. Finding the source of the matter-antimatter asymmetry would tell us why there is something rather than nothing. It would reveal a fundamental lopsidedness in reality's blueprint, a crack in perfect symmetry that allowed a universe of galaxies, stars, and conscious life to eventually emerge from the fire. That 1 in a billion surplus of matter set the stage for everything to come, but the story of our universe's birth holds an even more dramatic opening chapter. To solve several profound puzzles about the cosmos we see, theorists proposed an event of almost unimaginable violence in the very first instance of time. This is cosmic inflation, a concept so radical it reshaped our understanding of beginnings. The standard Big Bang theory left us with some troubling questions. Why is the universe so incredibly uniform in all directions? The temperature of the cosmic microwave background is the same everywhere to within a tiny fraction of a degree. Yet regions on opposite sides of the sky were never close enough to exchange heat or information. How could they reach the same temperature? Furthermore, why is the geometry of space so flat? Not flat like a sheet of paper, but in the sense that parallel lines stay parallel, indicating a perfect balance between the energy of expansion and the pull of gravity. These facts seemed like unlikely cosmic coincidences. Inflation solves them with a single, breathtaking idea. In the first trillionth of a trillionth of a trillionth of a second after the Big Bang, a strange, repulsive energy field, dubbed the inflaton field, took control of the universe. This field caused space itself to expand faster than the speed of light, not by moving things through space, but by stretching the very fabric of spacetime exponentially. In that fleeting moment, a subatomic speck of the primordial universe was blown up to a size larger than our entire observable cosmos today. This explains the uniformity. Before inflation, that tiny seed was a single connected region where everything was in contact. Inflation stretched it to become our entire sky, preserving that initial sameness. It also explains the flatness. Think of blowing up a balloon. A tiny, wrinkled patch on its surface becomes smooth and flat as the balloon expands. Inflation did that to the geometry of the universe, stretching any initial curvature until it appears perfectly flat to us. The theory is elegant and powerful, but it introduces its own profound mystery. What was the inflaton field? We have no idea what particle or force it represents. It is not part of our standard model. It switched on with unimaginable energy, drove the universe to double in size perhaps 100 times over, and then suddenly switched off, decaying into the hot soup of particles that would become our cosmic fireball. The only direct evidence we might find for this primeval event is a specific pattern imprinted on the cosmic microwave background, a faint swirl called primordial gravitational waves. These would be ripples in space-time itself generated by the violent tremors of inflation. Experiments like the Bicep telescope at the South Pole have hunted for this signature in the ancient light. A claimed detection in 2014 turned out to be cosmic dust, a sobering reminder of how difficult this search is. The lack of definitive proof is one challenge, but inflation leads to an even more staggering implication, one that pushes the boundaries of science itself. Because inflation, once started, may be eternal, the inflated field could decay in some regions, creating a bubble universe like our own, while continuing to expand exponentially everywhere else. This process could happen an infinite number of times, generating a vast multiverse, a cosmic froth of disconnected bubble universes, each with its own random set of physical laws and constants. In some, gravity might be strong and stars collapse instantly. In others, atoms may never form. We just happen to live in one where the numbers allow for galaxies and life. This idea is deeply controversial. If these other universes are permanently beyond our cosmic horizon, forever out of contact, is the multiverse a scientific theory or a philosophical speculation? It solves the puzzling fine-tuning of our universe's constants by invoking an infinite number of rolls of the dice, but for many physicists, a theory that cannot be tested, even in principle, resides in a troubling gray area. So we are left with a paradox. Inflation explains so much about our observable universe, yet its driving force remains a ghost, and its ultimate consequences may place the true nature of reality forever out of our reach. The ultimate fate of the cosmos hinges on a single unknown, the true nature of dark energy. Its behavior will write the final chapter for every star, planet, and atom in existence. Cosmologists have outlined 3 classical scenarios for how it all might end, and each one paints a profoundly different picture of eternity. The first is the Big Crunch, a dramatic reversal of the expansion. In this scenario, the density of matter and energy in the universe is so great that gravity eventually wins the long-term tug of war. The expansion would slow, halt, and then reverse, sending all galaxies rushing back toward each other. In a cosmic mirror of the Big Bang, the universe would collapse back into an unimaginably hot, dense singularity. Space and time themselves would come to an end. While a compellingly symmetrical idea, our measurements have all but ruled it out. The observed acceleration of expansion means gravity is losing, not winning. This leads us to the second, and currently most likely, fate, the Big Freeze, also called heat death. Here, dark energy remains constant or changes very slowly. The expansion continues forever, accelerating galaxies away from each other into an ever-deepening isolation. Over trillions of years, stars will exhaust their fuel, one by one, blinking out. Galaxies will fade to black. Even the massive black holes at their centers will slowly evaporate through a process called Hawking radiation. The universe will become a vast, ever-expanding graveyard, filled only with the faintest particles and radiation, stretched so thin that temperatures approach absolute zero. It is a quiet, cold, and lonely end, where all structure and energy gradients, the very things that allow for change and life, are smoothed away into a state of permanent, featureless equilibrium. But there is a third, far more violent possibility, the Big Rip. This scenario requires dark energy to be something more sinister than a cosmological constant. If its repulsive strength increases over time, its influence would grow. First, it would overcome the gravitational glue holding galaxy clusters together, flinging them apart. Then, billions of years later, it would tear individual galaxies to shreds. As the end draws near, the force would rip stars from their orbits and planets from their stars. In the final minutes, it would overcome the forces holding planets and stars together, shattering them. In the last horrific instance, even atomic and nuclear forces would be overwhelmed. Every molecule, every atom, every fundamental particle would be violently shredded, torn apart by the runaway stretching of space itself. The universe would end not with a whimper or a crunch, but with a catastrophic, instantaneous dissolution of all structure. Which of these fates awaits us? The answer is locked within the phantom of dark energy. Is it a constant feature of the vacuum, leading to the long, cold freeze? Or is it a dynamic, growing force, dooming us to the ultimate rip? Our telescopes are now measuring the expansion history of the universe with unprecedented precision, tracing how the acceleration has changed over billions of years, searching for any hint that dark energy is evolving. The mystery of our ultimate end is not a philosophical question. It is a physical one, and its solution lies in deciphering the deepest properties of the cosmos itself. The ultimate fate of the cosmos may be written in the phantom push of dark energy, but here in our own solar system, a different kind of ghost made its presence felt. For decades, two robotic pioneers whispered a secret that seemed to defy the very laws of gravity. The spacecraft Pioneer 10 and Pioneer 11, launched in the early 1970s, were humanity's first emissaries to the outer planets and beyond. After their historic flybys of Jupiter and Saturn, they continued their lonely journeys toward interstellar space. As they did, scientists tracking their radio signals noticed something deeply puzzling. Both spacecraft were slowing down ever so slightly more than they should have been. An unknown force equivalent to a 10 billionth of the gravity you feel on Earth was acting as a gentle but persistent brake. This was the Pioneer anomaly. The deceleration was minuscule, but it was there, a constant tug toward the sun that Newton and Einstein could not explain. For years, it haunted the edges of physics. Could it be a sign of new physics, perhaps a flaw in our understanding of gravity itself over vast distances? Some speculated about the gravitational pull of unseen dark matter in our solar system, or even the influence of other dimensions. The anomaly became a classic space mystery, a tiny data point with potentially universe-altering implications. The quest for an answer became a masterclass in scientific detective work. Teams of researchers scrutinized every possible conventional explanation. They calculated the faint pressure of sunlight on the spacecraft, the whisper of solar wind. They looked for fuel leaks from tiny thrusters or the outgassing of materials as the probes aged in the cold of deep space. Every conceivable systematic error was hunted down and measured. For a long time, nothing seemed to fit. The anomaly stubbornly remained. The breakthrough came not from exotic new physics, but from an extraordinary feat of historical reconstruction and thermal modeling. The key was heat. The Pioneers were powered by radioactive thermoelectric generators, which produced electricity from the decay of plutonium. This process also generated a lot of waste heat. The spacecraft were designed to radiate this heat away into space from their central compartments. Crucially, this heat radiation is not just light, it carries momentum. When a photon of heat bounces off the inside of the spacecraft and escapes in a particular direction, it gives the craft a tiny push in the opposite direction, like a minute rocket thruster. A team led by physicist Slava Turyshev realized that to model this effect perfectly, they needed to know the exact thermal blueprint of the decades-old spacecraft down to the smallest screw and wire. They launched a massive effort recovering old design documents, telemetry data, and even original software, piecing together a digital twin of the Pioneers. Their sophisticated model finally accounted for how heat was bouncing around inside the craft and radiating preferentially off the back of their large dish antennas, which were pointed back toward Earth and the Sun. This anisotropic or directionally uneven thermal radiation provided just enough of a constant sunward push to explain almost all of the anomalous deceleration. The ghost was, in the end, a reflection. The Pioneer anomaly stands as a profound cautionary tale and a testament to scientific rigor. It reminds us that the universe often speaks in whispers, and those whispers can be mistaken for the voice of new laws. It underscores the incredible precision required in deep space navigation, where a miscalculation the width of a single hydrogen atom per second can build into a major puzzle over decades. While largely resolved, a tiny fraction of the effect may still linger, a reminder that our models are never perfect. This relentless pursuit of a mundane explanation, this willingness to dig through decades of data to find a missing thermal photon, is what separates true science from speculation. It is the hard, unglamorous work that clears the path, ensuring that when we do finally hear a signal that truly breaks the rules, we will know it is not just our own machinery talking back to us. The meticulous accounting that solved the Pioneer puzzle only makes another, far stranger orbital mystery stand out in sharper relief. This one does not occur in the deep, quiet dark of interstellar space, but in the bustling orbital neighborhood of our own planet. It is called the flyby anomaly, and it is a ghost in the machinery of our most precise celestial navigation. When spacecraft perform a gravitational slingshot maneuver around Earth, using our planet's gravity to steal momentum and change their course, their speed is calculated down to the millimeter per second. Yet on several occasions, these spacecraft have emerged from behind Earth with a tiny, unexpected boost or break. Their measured velocity does not match the prediction. The first notable case was the Galileo spacecraft in 1990. On its long journey to Jupiter, it swung by Earth for a gravity assist. When it re-established contact after the flyby, tracking data showed it had gained about 4 millimeters per second of extra speed. That is slower than a crawling ant, but in the exquisitely precise realm of orbital mechanics, it was a glaring discrepancy. The same thing happened with the near-Shoemaker spacecraft in 1998, which gained an unplanned 13 millimeters per second during its Earth flyby. Other missions like Rosetta and Messenger showed smaller but similar anomalies. Each time the pattern was baffling. The effect seemed to depend on the spacecraft's trajectory, appearing stronger during certain flyby geometries, particularly when the craft's incoming and outgoing paths were asymmetrical relative to Earth's equator. Scientists immediately searched for conventional culprits. Could it be atmospheric drag even at high altitude? The effect was checked and dismissed. The spacecraft were far too high. What about the pressure of radio waves from Earth's deep space network on the spacecraft's large antennas? Meticulous calculations showed this radiation pressure was far too weak. The influence of Earth's magnetic field, tidal forces from the Moon and Sun, even the slight bulge of Earth's equator were all examined. None could account for the full anomaly. This left the door open to more radical ideas. Some physicists suggested it might be a hint of modified gravity, a subtle deviation from Einstein's theory of general relativity that only becomes noticeable in specific orbital conditions. Others proposed it could be an effect of Earth's rotation dragging spacetime around with it, an effect called frame dragging, but the measured anomaly was hundreds of times larger than that theory predicts. The most exotic suggestions ventured into unseen dimensions, proposing that the spacecraft might be interacting with hidden aspects of reality that subtly alter its momentum. The frustrating truth is that the flyby anomaly remains an open case. Unlike the Pioneer puzzle, a single, satisfying conventional explanation has not been found. Part of the problem is data. These flybys are rare, high-stakes events, not controlled laboratory experiments. Each spacecraft is unique in its shape, mass, and orientation, making it difficult to isolate a pure signal. Some later missions, like the Juno spacecraft's flyby in 2013, were specifically instrumented to look for the anomaly and showed no unexpected velocity change, deepening the mystery. Was the anomaly real, or was it a subtle artifact of how we tracked older spacecraft? Could it be that the effect is real but depends on variables we have not yet identified, like the craft's spin or the precise distribution of its internal fuel? This unsolved puzzle in orbital mechanics is a tantalizing whisper. It is a reminder that even here in our own celestial backyard, the universe might still be playing by rules we have not fully read. Every unexplained millimeter per second is a question mark hanging in the void, a tiny but persistent suggestion that our map of gravity, the force that literally holds the cosmos together, might still have a few blank spaces waiting to be filled. While our own spacecraft whispers secrets in the solar wind, a single, deafening shout once pierced the cosmic silence from far beyond. In the early evening of August 15, 1972, the Big Ear radio telescope at Ohio State University was engaged in its routine, patient sweep of the sky, listening for any signal that stood out from the universal static. It was a project in the search for extraterrestrial intelligence, scanning frequencies near the hydrogen line, a quiet band of the radio spectrum considered a logical channel for interstellar communication. For 72 seconds, as the telescope's fixed dish slowly scanned past a point in the constellation Sagittarius, its receivers recorded something extraordinary. It was a strong, narrowband radio signal, precisely the kind of signature a purposeful, technological broadcast would produce. It rose in intensity to a peak and then faded away, exactly as expected for a signal from a fixed point in space passing through the telescope's stationary beam. The data was printed out on line after line of alphanumeric characters, where signal strength was represented by numbers and letters. The next day, volunteer astronomer Jerry Amon was reviewing the computer printout. His eyes locked onto a sequence on one line, 6 characters long, 6X0J10. In the system used, the letters represented numbers 10 through 35. The sequence X translated to the values 26, 31, 30. This was an intensity spike 30 times louder than the background noise of deep space. It was a perfect artificial sounding needle in a cosmic haystack. Stunned, Amon took his red pen and circled the anomalous sequence. In the margin, he wrote a single, heartfelt word of pure astonishment: "Wow." That exclamation gave the signal its immortal name. The WOW signal was everything SETI researchers had hoped to find. It was narrow in frequency, meaning it occupied a very specific radio channel, unlike the broad noise of natural cosmic objects. It appeared and disappeared with the telescope's motion, confirming it came from a specific location in space, not a local source like a passing airplane or a terrestrial transmitter. For that brief window, it was the most compelling candidate for an extraterrestrial message ever detected. And then it was gone. Follow-up observations by Big Ear and other telescopes scanning the same patch of sky for decades heard nothing. Not a whisper, not an echo, the signal never repeated. This one-off nature is the heart of the mystery. A civilization trying to get our attention would likely broadcast a repeating signal, a persistent beacon. So why did we hear it only once? The hunt for a natural explanation began. Could it have been a secret military transmission reflected off space debris? Possibly, but no known satellite or aircraft matched its profile. In 2016, a researcher proposed it might have been caused by hydrogen clouds surrounding 2 passing comets in that region of the sky. The idea gained brief attention but was swiftly dismissed by astronomers, including Amon himself. The comets were not in the telescope's field of view at the time, and their diffuse hydrogen would not produce such a powerful, narrowband spike. The WOW signal stands alone, a perfect cosmic cipher. It was too perfect to be easily dismissed as noise, yet too fleeting to ever be verified. It is the quintessential SETI enigma, a single, brilliant flash in the pan that has fueled both scientific curiosity and public imagination for over half a century. It serves as a haunting reminder of the challenge we face. The universe is vast and our window of listening is infinitesimally small. We might be like a lighthouse keeper who, glancing out at the ocean for 1 second each night, catches a single, distant flash from a ship that is never seen again. Was it a real vessel or a trick of the light? The WOW signal keeps the profound question alive, not with an answer, but with the enduring, tantalizing possibility that for 72 seconds in 1972, we were not alone in the universe. The profound silence that followed the WOW signal taught us that cosmic messages might be fleeting, but the universe has since revealed it speaks in many other explosive languages. Among the most startling is a phenomenon that turns the entire sky into a strobe light of unimaginable power. They are called fast radio bursts, and in the span of a single blink, one can outshine 500 million suns. For a few milliseconds, a source from a galaxy billions of light years away unleashes a torrent of radio waves carrying more energy than our sun emits over 80 years. Then, just as suddenly, it vanishes back into the quiet. The first of these bursts was discovered in archival data in 2007, a solitary spike so bizarre that for years astronomers debated if it was a glitch in the telescope's electronics or a local microwave oven being opened mid-observation. But then more were found, each with a distinctive fingerprint. Their radio waves are scattered and delayed, a telltale sign of having traveled through the diffuse gas between galaxies, allowing us to measure their incredible cosmic distances. The mystery deepened with a monumental discovery in 2016. A burst from a dwarf galaxy 3 billion light-years away did something unprecedented. It repeated. Unlike the singular, catastrophic events that produce one-off bursts, this source, named FRB 2012110-2A, flashed again and again. It was not a final death cry, but a periodic, angry heartbeat from across the universe. This changed everything. A repeating source cannot be the result of a one-time cataclysm like two neutron stars crashing together and destroying themselves. It must be powered by an object that survives the eruption, something that can fire off these monstrous shots repeatedly. The prime suspect now is a magnetar, a type of neutron star with a magnetic field so intense it could erase a credit card from halfway to the moon. Theorists suggest that starquakes on the surfaces of these hypermagnetic corpses, or sudden magnetic reconnection events similar to solar flares but a trillion times more powerful, could generate the staggering energy we see. Yet even this compelling idea faces challenges. Some observed bursts show complex structures with multiple sub-pulses within the millisecond flash, hinting at a highly ordered engine. The most speculative and captivating possibility is that we are seeing the signatures of advanced technology. Could a burst be the leakage from a massive interstellar propulsion system, a light sail powered by a planet-sized radio transmitter, or perhaps a beacon deliberately aimed? While natural explanations are far more likely, the sheer power and brevity of FRBs force us to confront the scale of what might be possible in the cosmos. What is certain is that we are now in a golden age of detection. Dedicated telescopes like CHIME in Canada are scanning the entire northern sky daily, catching dozens of new bursts every month, some from sources closer to home. Each new detection is a data point, helping us triangulate their host galaxies and understand the environments that breed such violence. Fast radio bursts have transformed from a curious anomaly into a fundamental tool for cosmology. By measuring how their signals disperse through the invisible matter between galaxies, we are essentially weighing the universe, mapping the cosmic web that normal telescopes cannot see. They are both a profound mystery and a powerful new probe, flashes in the cosmic dark that illuminate the structure of everything. That single, unexplained flash from the WOW signal only deepens a much older and more profound silence. If the universe is so vast and ancient, brimming with hundreds of billions of galaxies, each with hundreds of billions of stars, then where is everybody? This is the essence of the Fermi paradox, named for physicist Enrico Fermi, who over a casual lunch in 1950 is said to have posed the simple, devastating question. The numbers are overwhelmingly on the side of cosmic company. Even if only a tiny fraction of stars host habitable planets, and a tiny fraction of those give rise to life, and a tiny fraction of that life becomes intelligent, the galaxy should be teeming with civilizations. By some estimates, there should be thousands, even millions of advanced societies in the Milky Way alone. Our radio telescopes should be drowning in their chatter, our skies patterned with their artifacts. Instead, we hear only a deafening cosmic quiet. This contradiction between high probability and zero evidence is one of the most unsettling mysteries we face. It forces us to consider terrifying and wonderful possibilities about the nature of life and intelligence in the cosmos. One of the most sobering solutions is the concept of the Great Filter. This idea suggests that somewhere between the initial conditions for life and the emergence of a galaxy-spanning civilization, there is a step, a barrier that is almost impossible to pass. It could be that the origin of life itself is a miraculous fluke far rarer than we think. Perhaps the leap from simple single-celled organisms to complex, multicellular life is the immense hurdle. The fossil record shows life stayed simple for billions of years before that jump. Or the filter could lie ahead of us. It might be that technological civilizations inevitably destroy themselves with their own creations, be it nuclear war, engineered plagues, or runaway artificial intelligence. The haunting implication is that if the filter is in our past, we are a cosmic miracle. But if it is in our future, our apparent loneliness is a grim omen of what awaits. A less ominous but equally strange idea is the zoo hypothesis. Imagine a galactic civilization, ancient and wise, that has long known about our young, turbulent world. They have placed us in a kind of interstellar nature preserve with a strict policy of non-interference. They observe from a distance, allowing us to develop naturally, only making contact when we reach a certain level of maturity or make the first move ourselves. To them, our planet might be a living museum, a fragile ecosystem of emerging intelligence to be protected from contamination. This would explain the silence, but it casts humanity in a strangely passive role, like animals in a cage unaware of the zookeepers. Then there are the practical limitations. The sheer distances between stars are almost incomprehensible. Traveling even to our nearest neighbor, Proxima Centauri, with current technology would take tens of thousands of years. The energy required for faster travel is astronomical. Perhaps civilizations simply find it more efficient to stay home, exploring virtually or tending to their own worlds. Or maybe they communicate in ways we cannot yet perceive, using neutrino beams or quantum entanglement, technologies that are still magic to us. Their signals might be all around us, but we lack the ears to hear them. Ultimately, the great silence holds up a mirror. It forces us to ask not just where they are, but what we are and what we might become. Are we the first to look up and wonder, pioneers in a young, quiet galaxy? Or are we the last, surrounded by the silent ruins of those who came before? The paradox has no answer yet, but in searching for one, we are ultimately defining the story of humanity, wrestling with our own potential for longevity, wisdom, and survival in a universe that remains stubbornly, mysteriously mute. That profound cosmic silence forces us to look for signs of intelligence in more subtle ways, not in radio signals, but in the very architecture of starlight. And in 2015, astronomers found something that seemed to fit that description perfectly, a star that behaved like nothing else in the galaxy. Its official designation is KIC 8462852, but the world came to know it as Tabby's star, named after the astronomer Tabitha Boyajian who led its investigation. Data from NASA's Kepler telescope, which stared at one patch of sky for years to detect the tiny, periodic dips of planets crossing their stars, revealed a pattern around this star that defied all logic. Instead of the neat, repeating dips of an orbiting world, Tabby's star showed erratic, dramatic plunges in brightness. one event dimmed the star by a staggering 22%. To put that in perspective, if a Jupiter-sized planet passed in front of this sun-like star, it would block only about 1% of the light. Something was blocking a quarter of this star's face, and it was not a simple sphere. The dips were asymmetric, with sharp drops and slower recoveries, and they did not repeat on a predictable schedule. The light curve looked less like a planet transit and more like someone was throwing a chaotic assortment of shapes in front of the star. The hunt for an explanation began, and the natural possibilities were all deeply strange. One early hypothesis involved a giant swarm of comets, thousands of them, perhaps disturbed by a passing star, now on long, elliptical orbits that would occasionally cluster together to block the light. This could explain the irregular timing and the deep dips, but it required an almost implausible number of comets, a family of them on a scale never before observed. Another idea pointed to circumstellar dust, a massive, clumpy ring of debris orbiting the star. The dust would block shorter wavelengths of light more than longer ones, and indeed, Tabby's star dimmed more in blue light than in red, a clue that pointed to something diffuse like fine grains. Perhaps a recent catastrophic collision between planets had filled the system with a cloud of shattered rock and dust, creating this bizarre shadow play. But then came the hypothesis that captured the public's imagination. What if we were seeing the shadows of an alien megastructure? The concept, first proposed by physicist Freeman Dyson, is known as a Dyson sphere. An advanced civilization, having harnessed all the energy of its planet, might eventually seek to capture the entire energy output of its star. They could construct a vast swarm of solar-collecting satellites or panels in orbit around their sun, a megastructure that would partially block the star's light from our perspective. The irregular, jagged dips of Tabby's star could, in theory, be the silhouettes of such an incomplete, under-construction swarm, a colossal project on a stellar scale. It was a breathtaking idea, but scientists are trained to follow Occam's razor, the principle that the simplest explanation is usually the correct one. An alien megastructure is the least simple explanation imaginable. Further observations revealed the star was also dimming very slightly over years, a long-term fade that added another layer of mystery but also pointed toward natural dust. Crucially, when the star dipped, it dimmed more in some colors than others, which is exactly what fine, microscopic dust does, but not what a solid, opaque megastructure would do. A solid object would block all colors of light equally. The current scientific consensus leans heavily toward a natural, if extraordinarily rare, astrophysical phenomenon. The leading theory now suggests the star is surrounded by a massive, uneven ring of dusty debris, possibly from the slow disintegration of a moon or a shattered planet, creating a complex and evolving cloud that passes between us and the star. Tabby's star remains a mystery, but it taught us a vital lesson in cosmic detective work. It showed us that the universe can produce signals so bizarre they brush against the edges of science fiction, forcing us to confront our own hopes and assumptions. While the megastructure dream fades, the reality is perhaps more profound. We discovered a new class of stellar behavior, a reminder that for every answer we find, the cosmos has a dozen new, even weirder questions waiting in the dark. The bizarre light of Tabby's star showed us that strange shadows can have natural causes, but just 1 year later, a shadow of a different kind raced through our own celestial neighborhood. In October 2017, the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at breathtaking speed. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. This was not an asteroid from our solar system. It was a visitor from the interstellar void, the first object ever confirmed to have originated around another star. We named it Oumuamua, Hawaiian for scout or messenger from the distant past. As astronomers frantically trained their telescopes on this cosmic interloper, its strangeness only grew. First was its shape. By measuring how its brightness changed dramatically as it tumbled, scientists inferred its form. It was not round like a typical asteroid or comet. It was extraordinarily elongated, perhaps 10 times as long as it was wide, resembling a cigar or a pancake. Nothing naturally occurring in our solar system looks quite like that. Then there was its motion. As it whipped around the sun and began its exit back into interstellar space, precise tracking revealed a tiny but significant anomaly. It was accelerating ever so slightly on its way out. This is something comets do as sunlight vaporizes their icy surfaces, creating a jet of gas that acts like a tiny rocket engine. But when we looked at Oumuamua, we saw no coma, no cloud of gas and dust, no tail streaming behind it. It showed absolutely no visible signs of outgassing. It was as dark and inert as a rock, yet it was behaving like a comet. This non-gravitational acceleration became the central puzzle. The scientific community scrambled for natural explanations. Could it be a shard from a Pluto-like planet in another star system, a fragment of frozen nitrogen blasted off by some ancient cataclysm? As it neared the sun, the theory went, sunlight would have vaporized this nitrogen ice from its surface, providing the thrust we saw, without producing the dusty coma of a water ice comet. Another idea proposed it was a hydrogen iceberg, a chunk of solid molecular hydrogen that could sublimate invisibly. Yet hydrogen ice is incredibly fragile and would likely not survive the long journey between stars. Each natural hypothesis explained one oddity but struggled with others. The shape, the acceleration, and the lack of visible activity together formed a perfect storm of weirdness. This confluence of anomalies led one prominent astronomer, Avi Loeb, to float a more speculative possibility. Could Oumuamua be artificial in origin? Perhaps it was a piece of alien technology, a discarded light sail from another civilization, drifting through the galaxy. The idea was that a thin, wide light sail, pushed by the radiation pressure of starlight, could account for both the strange shape and the non-gravitational acceleration without any visible outgassing. While most astronomers strongly favor a natural origin, citing the principle that extraordinary claims require extraordinary evidence, the debate itself was illuminating. It forced us to confront how little we know about the formation and variety of objects in other star systems. Our solar system's inventory of asteroids and comets is just one sample. Oumuamua was a messenger telling us that other planetary systems can build things we have never seen before. Its fleeting visit, lasting only weeks before it became too faint to observe, was a wake-up call. It revealed that our solar system is constantly being traversed by interstellar material. We simply never had the telescopes to see it before. Oumuamua was the first, but it will not be the last. In 2019, we detected a second interstellar visitor, Comet Borisov, which looked and behaved much more like a familiar comet. This told us that interstellar space is filled with a diverse menagerie of objects. New observatories like the Vera C. Rubin Observatory, coming online soon, will scan the entire sky nightly and are expected to find many more of these visitors each year. Each one will be a pristine sample from another star, a chance to hold a piece of another world in our data. They are cosmic driftwood carrying the chemical signatures of their birth clouds far away. The true legacy of Oumuamua is not a single answer, but a new direction for exploration. It opened our eyes to the traffic passing through our own backyard, reminding us that we are not an isolated island, but part of a dynamic, interconnected galactic ecosystem. The interstellar driftwood passing through our system reminds us we are part of a much larger structure. But what if that structure itself shows a strange and unexpected alignment? This brings us to one of the most unsettling statistical ghosts in modern cosmology, a pattern so unnerving that scientists gave it a dramatic name, the axis of evil. It is a mystery written in the oldest light in the universe, the cosmic microwave background. This faint afterglow, a snapshot of the universe when it was just 380,000 years old, is the cornerstone of modern cosmology. Its temperature is nearly uniform, but not perfectly so. Tiny fluctuations, mere millionths of a degree, are imprinted across the sky, the seeds from which all galaxies would later grow. These fluctuations should be random, like a static pattern on an old television with no preferred direction. The universe, according to our most cherished principle, should look the same in all directions. This is the assumption of isotropy, a cornerstone of the Copernican principle that says we do not occupy a special place. Yet, when scientists created a detailed map of this ancient light, they found something that sent a chill through the field. Certain large-scale patterns in the temperature fluctuations, features spanning billions of light-years, appeared to be mysteriously aligned. Their axes seemed to correlate, not with some grand cosmic structure, but with the plane of our own solar system. It is as if the universe's oldest fingerprint is subtly pointing toward us. This should be impossible. The cosmic microwave background comes from a time long before our solar system, or even our galaxy, existed. Its patterns were set when the observable universe was the size of a grapefruit. There is no physical mechanism for those primordial ripples to know or care about the orientation of a tiny planetary system that would not form for another 9 billion years. The implication is deeply troubling. One possibility is that there is an unknown source of contamination locally, within our own Milky Way or even our solar system, that is subtly distorting the signal. Perhaps dust or some other foreground emission is imitating a cosmological pattern. Teams have searched exhaustively for such a contaminant, but none has been found that fully explains the alignment. If it is not local dirt on the lens, then we are forced to consider far more radical ideas. Could it be a sign that the universe is not isotropic on the largest scales? This would mean the Big Bang was not perfectly uniform, that there was a preferred direction woven into the fabric of space-time itself. Such a finding would require a complete rewrite of our standard model of cosmology. Or, most unsettling of all, could it be evidence that we do occupy a special place, a direct challenge to the Copernican principle that has guided astronomy for centuries? The name axis of evil was coined half in jest, reflecting how this anomaly seems to undermine the beautiful, random simplicity of our models. Many scientists believe it is likely a statistical fluke, a cosmic coincidence that our most sensitive measurements have now revealed. As our maps of the CMB grow more precise from missions like Planck, the significance of the alignment has appeared to weaken, though not completely vanish. Yet it persists as a nagging whisper in the data, a reminder that our most fundamental assumptions about the universe's uniformity are based on inference, not absolute proof. Every time we look at the smooth, isotropic universe in our textbooks, the axis of evil sits in the background, a quiet question mark about whether we are truly seeing the cosmos as it is, or merely the reflection of our own unexpected place within it. While the axis of evil questions the largest scales, another profound crack in our cosmic model appears at the smallest. It is a mystery of missing material, not on a galactic scale, but on the scale of atomic nuclei. This is the lithium problem, and it threatens our otherwise triumphant story of the universe's first minutes. Our account of the Big Bang's immediate aftermath is a masterpiece of predictive power. In a process called Big Bang nucleosynthesis, the entire cosmos was a searing hot nuclear fusion reactor. For a brief window between about 1 second and 20 minutes after the beginning, protons and neutrons slammed together, forging the first atomic nuclei. Our theoretical models of this primordial cooking predict with stunning accuracy the amounts of the lightest elements we should see today. The predicted abundance of hydrogen and its heavy isotope, deuterium, matches perfectly with what we observe in the oldest, most pristine corners of space. The predicted amount of helium-4 is spot on, but for one element the math goes wrong. The models say there should be about 3 times more lithium-7 in the universe than we actually find. We are missing 2/3 of the cosmos's third lightest element. This is not a small rounding error. It is a glaring discrepancy that has persisted for decades, a stubborn outlier in an otherwise perfect theory. So where did all the lithium go? One possibility is that our understanding of nuclear physics in that extreme environment is incomplete. Perhaps there were unknown nuclear reaction pathways in the early universe that destroyed lithium as quickly as it formed, or converted it into other elements. Physicists have meticulously recalculated every known reaction rate, but the gap remains. Could there be a rare, forgotten reaction waiting to be discovered that resolves the issue? Another avenue points to the stars, the oldest stars in our galaxy, which formed from nearly pure primordial gas, show the same lithium deficit. This suggests the destruction happened early. Perhaps these ancient stars themselves are the culprits. As they churn their interiors, lithium, which is fragile and burns at relatively low temperatures, could have been transported deep into the stellar cores and destroyed over billions of years. But modeling this mixing process to account for the exact uniform shortfall seen across many stars is a complex challenge. Then there are the more exotic solutions. Could entirely new physics be at play? Some theorists have proposed that the presence of unknown particles in the early universe, like certain types of dark matter, could have interacted with the primordial soup and altered the nuclear reaction yields, selectively depleting lithium. Others have even suggested that our measurements of the primordial lithium abundance might be systematically wrong, though this seems increasingly unlikely as data from more ancient stars accumulates. The lithium problem is a classic scientific puzzle. It is not a crisis that overturns our entire model, but a precise, nagging inconsistency. It tells us that our otherwise flawless picture of the universe's first 20 minutes has a tiny, unexplained blemish. Solving it might require just a subtle tweak to a nuclear cross-section, or it might be the thread that leads us to a deeper layer of particle physics, hidden within the furnace of creation itself. It is a reminder that even our greatest successes hold secrets, and that the universe's first recipe might have had one ingredient or one step we have yet to fully understand. The universe's very first recipe may have a subtle flaw, but our measurements of its current expansion are facing a far more glaring contradiction. This is the Hubble tension, and it is not just a minor discrepancy. It is a full-blown crisis at the heart of modern cosmology, a direct conflict between two of our most trusted ways of measuring the cosmos. The Hubble constant is a single, crucial number. It tells us how fast the universe is expanding right now, the current rate at which galaxies are rushing apart. For decades, astronomers have been refining this measurement, and they have settled on two primary, independent methods. The first method looks back to the dawn of time, using the cosmic microwave background, that ancient afterglow from the infant universe. By studying its intricate patterns, we can calculate the ingredients of the early cosmos, the amounts of dark matter, dark energy, and ordinary matter, and run the cosmic film forward to predict what the expansion rate should be today. This is the early universe method, and it gives us a very precise answer. The second method works in our own cosmic backyard, measuring the universe's expansion directly. Astronomers use celestial landmarks called Cepheid variable stars. These stars pulse with a rhythm that is directly tied to their true brightness. By measuring their pulse rate, we know their intrinsic brightness. Then, by observing how dim they appear to us, we can calculate their exact distance, just as you can tell how far away a car is by how faint its headlights seem. We chain these Cepheid distances to even brighter cosmic explosions, type I a supernova, which act as standard candles across vast distances. By watching how fast galaxies containing these supernovae are receding from us, we get a direct, local measurement of the Hubble constant. This is the late universe method, and it too is exquisitely precise. Here is the problem. These two numbers do not agree. The local measurement, using stars and supernova, says the universe is expanding faster than the early universe measurement predicts. The gap is not large, only a few percent, but after years of increasingly sensitive observations, the statistical significance of this mismatch has grown. It is now far too big to dismiss as a simple error. It is a persistent, stubborn signal that something in our understanding is fundamentally wrong. So, what could it be? One possibility is that there is a hidden systematic error in one of the measurements, perhaps in our understanding of the Cepheid stars themselves or in the intricate physics of the supernova. Teams are obsessively checking and rechecking every step. Yet, as the measurements become more independent using different telescopes, different stars, even different geometric methods, the tension not only remains, it tightens. This leads to the far more exciting possibility. We are seeing the first cracks in our standard model of cosmology. The universe might be trying to tell us that our picture of its history is incomplete. Perhaps dark energy is not a constant, but evolved over time in a way we have not accounted for. Some theorists propose an injection of early dark energy in the universe's first few 100,000 years, a brief surge that would have altered the primordial sound waves imprinted on the CMB, changing the predicted expansion rate today. Others look to the ghostly neutrino. What if these particles have unexpected properties like a greater mass or interactions with dark matter that could subtly change how structures formed in the early universe? The Hubble tension is more than a technical disagreement. It is a direct challenge, a cosmic tug of war between the story told by the universe's first light and the story told by the stars we see around us today. One of these stories, or perhaps both, contains a chapter we have not yet read. Resolving this crisis will either expose a flaw in our most precise instruments or, more thrillingly, force us to rewrite the laws that govern the cosmos itself. The Hubble tension reveals a crack in our cosmic model, but there is a place where our two most successful theories of reality break down completely. This is the domain of the black hole, where gravity becomes so strong that not even light can escape. Within these cosmic pits, a paradox so profound it has divided physicists for decades lies waiting. It is the black hole information paradox, and it asks a deceptively simple question. When something falls into a black hole, is all information about it lost forever? Our two pillars of physics give contradictory answers. Quantum mechanics, the rulebook for the very small, states with absolute certainty that information can never be destroyed. It can be scrambled, hidden, or transformed, but it must always be preserved in principle. General relativity, Einstein's theory of gravity that describes the cosmos, paints a different picture. It says that when matter crosses a black hole's event horizon, the point of no return, it is lost to our universe. All the intricate details about that matter, whether it was a star, a spaceship, or a library of books, are crushed into the singularity at the black hole's heart. To the outside universe, a black hole can be described by just three simple numbers: its mass, its electric charge, and its spin. Everything else, all the information that made the infalling matter unique, is erased. For decades, this was an unsettling philosophical puzzle. Then Stephen Hawking made it a concrete crisis. In the 1970s, Hawking applied quantum theory to the space just outside a black hole's event horizon. He found that the intense gravitational field could spontaneously create pairs of particles from the fabric of empty space. Normally, such particle-antiparticle pairs pop into existence and annihilate each other almost instantly. But at the edge of a black hole, one particle could fall in while the other escapes. To an outside observer, the black hole appears to be emitting a faint glow of radiation, now called Hawking radiation. This radiation is purely thermal, like the heat from a stove. It contains no specific information about what is inside the black hole. It is random noise. Here is the paradox. Hawking radiation causes black holes to slowly lose mass and evaporate. Over unimaginable eons, a black hole could completely evaporate away, leaving behind only this thermal radiation. If that happens, then all the information about everything that ever fell into the black hole has vanished from the universe. Quantum mechanics says this is impossible. We are left with a fundamental contradiction. Either our understanding of quantum law is wrong, or our picture of black holes from general relativity is incomplete. The search for a resolution has led to some of the most mind-bending ideas in theoretical physics. One revolutionary concept is the holographic principle. It suggests that all the information about what falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across its surface. The three-dimensional interior is a projection of that information, much like a hologram that gives the illusion of depth from a flat surface. In this view, when Hawking radiation is emitted, it carries away information imprinted on the horizon, scrambled beyond recognition but not destroyed. Another possibility is that evaporation stops at the last moment, leaving behind a tiny, stable remnant, a fossil containing all the compressed information. Yet this idea brings its own problems, like how an infinite amount of information could be stored in a vanishingly small object. Perhaps the most satisfying potential answer is that our initial assumption about Hawking radiation is flawed. Maybe the radiation is not purely thermal after all. Through incredibly complex quantum interactions, the information about the infalling matter could be subtly imprinted onto the escaping radiation, like a message hidden in static. Decoding that message would be virtually impossible for us, but the information would, in principle, be preserved. This paradox is more than a technical debate. It is a battle for the soul of physics, a direct clash between our understanding of the infinitesimally small and the unimaginably large. Solving it may require a theory of quantum gravity, a framework that unites these two disjointed rulebooks into one. The black hole is not just a cosmic vacuum cleaner. It is the ultimate laboratory, testing the limits of our knowledge and forcing us to question whether the universe truly forgets. If black holes are the universe's ultimate information shredders, then the cosmos also possesses its own natural particle accelerators, capable of launching subatomic bullets with almost inconceivable force. These are ultra-high-energy cosmic rays, and they represent one of the most baffling delivery mysteries in all of astrophysics. Imagine a single proton, a tiny fragment of an atom traveling through space. Now imagine it carrying the kinetic energy of a professionally thrown baseball, all compressed into that one minuscule particle. This is not science fiction. Such particles, with energies exceeding 100 million trillion electron volts, regularly slam into Earth's upper atmosphere. They possess millions of times more energy than anything we can produce in our most powerful human-made accelerators, like the Large Hadron Collider. The sheer power involved is staggering. A single one of these cosmic rays carries the punch of a medium-sized meteoroid, but delivered by something a trillion times smaller. The fundamental question is simple yet profound. What natural engine in the universe can possibly launch a proton to such insane speeds? The hunt for these cosmic accelerators is complicated by a fundamental property of the particles themselves. Unlike neutral light or gravitational waves, cosmic rays are electrically charged, mostly protons or atomic nuclei. This means that as they streak across the galaxy and beyond, they do not travel in straight lines. The weak but pervasive magnetic fields that fill interstellar and intergalactic space act like a cosmic funhouse of mirrors, bending and twisting their paths incessantly. By the time one of these ultra-high-energy particles finally collides with our atmosphere, creating a vast cascade of secondary particles we can detect, its original direction is completely scrambled. We see the spectacular splash, but we have lost all trace of the gun that fired the bullet. So we must become cosmic detectives, reasoning backwards from the sheer energy required to narrow down the list of suspects. Any viable source must be an environment of almost unimaginable violence, capable of focusing energy into a single particle with ruthless efficiency. The prime suspects are the most energetic phenomena we know. At the top of the list are active galactic nuclei, the monstrously bright cores of galaxies powered by supermassive black holes feeding on surrounding matter. The relativistic jets screaming away from these black holes could, in theory, act as perfect particle accelerators on a galactic scale. Another candidate is the gamma-ray burst, the universe's most powerful explosion since the Big Bang itself. The catastrophic collapse of a massive star or the merger of two neutron stars could create shockwaves powerful enough to impart these tremendous energies. Some scientists look closer to home, to starburst galaxies where frantic waves of star birth and death create a turbulent soup of supernova remnants and stellar winds, potentially combining their forces to reach these extreme energies. To solve this mystery, scientists built the world's largest cosmic ray detector, the Pierre Auger Observatory in Argentina. It is not a single telescope, but an array covering an area of 3,000 square kilometers, about the size of Rhode Island. It uses 1,600 water tanks to detect the secondary particles from air showers, while 24 fluorescence telescopes watch the faint ultraviolet glow the shower produces in the night sky. This hybrid approach allows Auger to measure both the energy and the rough incoming direction of these rare events with unprecedented accuracy. The observatory has made critical progress, finding that the highest energy cosmic rays do not arrive uniformly from all directions. There is a slight anisotropy, a statistical leaning suggesting they originate from outside our own Milky Way galaxy. Yet, despite collecting data for nearly 2 decades, Auger has not been able to point definitively to a single source or even a specific class of object. The particles are simply too rare and the magnetic deflections too great for a clear fingerprint. The mystery of ultra-high-energy cosmic rays is a perfect storm of cosmic scale and fundamental physics. We are being bombarded by messengers from the most violent places in existence, but their letters have been torn up and scattered by magnetic winds during their billion-light-year journey. Deciphering their origin is not just about cataloging cosmic monsters. It is a direct test of our understanding of particle acceleration in the most extreme environments, a challenge to see if we can finally read the return address on the universe's most energetic mail. These cosmic bullets are dwarfed by the sheer magnetic fury of a star that did not simply die, but transformed into a monster. When a massive star goes supernova, its core can collapse into a city-sized sphere of pure neutronium, a neutron star. But a rare few of these stellar corpses are born spinning furiously and possess a magnetic field of almost incomprehensible power. These are magnetars, and they possess the strongest magnetic fields in the known universe. To grasp the scale, picture a simple refrigerator magnet. Its field is about 100 times stronger than Earth's own magnetic field. A medical MRI machine creates a field thousands of times stronger than that. A magnetar's field is a quadrillion times stronger than Earth's. That is a 1 followed by 15 zeros. At a distance of 100,000 kilometers, the distance from Earth to the Moon, a magnetar's magnetic field would effortlessly strip the information from every credit card on our planet. It is a force so intense it warps the very structure of matter itself, squeezing atoms into long, thin needles. This unimaginable magnetism does not lie dormant. It fuels cataclysmic violence. The crust of a neutron star is a lattice of iron nuclei, a material 10 billion times stronger than steel. Yet the titanic magnetic stress can fracture this crust, causing starquakes. When it does, the magnetar releases a giant flare in a fraction of a second, unleashing more energy than our sun emits in 100,000 years. We see these eruptions as soft gamma-ray repeaters, terrifying bursts of high-energy light. Their power is so immense that on August 27, 1998, a magnetar flare from 20,000 light-years away actually disturbed Earth's upper atmosphere, briefly ionizing it and affecting long-range radio communications. It was a celestial shout loud enough to be felt across the galaxy. The central mystery is how such a magnetic field is generated and sustained. The leading theory is the dynamo model. If a newborn neutron star is spinning fast enough, perhaps hundreds of times per second, the turbulent convection of its super-hot, superfluid interior could act like a colossal generator, amplifying a pre-existing stellar magnetic field to these ludicrous levels. But the details are murky. Does the field reside in the superconducting core, or is it anchored in the rigid crust? How does it slowly decay over millennia, and what triggers the sudden, catastrophic rearrangements that cause the flares? Magnetars are now prime suspects in solving other cosmic puzzles. Their explosive nature makes them a compelling source for at least some fast radio bursts. A single colossal crustal crack or a sudden magnetic reconnection event on a magnetar could, in theory, produce the staggering millisecond flash of radio energy we detect from distant galaxies. They are also natural laboratories for physics under conditions we could never hope to recreate. They allow us to study quantum electrodynamics, the behavior of matter and magnetic fields, at energy densities that existed only a microsecond after the Big Bang. By observing the slow, steady spin down of a magnetar as its magnetic field breaks its rotation, or by catching the X-ray pulses from hotspots on its surface, we are probing the limits of material strength and the very nature of the neutron star interior. A magnetar is a testament to the fact that death in the cosmos is not an end, but a transformation into something even more extreme. It is a reminder that the universe is not just vast and empty, but filled with engines of unimaginable ferocity, where the simple force of magnetism becomes a world-breaking power. We have accounted for the ghostly dark matter, and yet a different kind of cosmic inventory has come up short. This is the missing baryon problem, and it is a mystery of misplaced ordinary stuff. Baryons are the particles that make up everything you see, the protons and neutrons in every atom of every star, planet, and person. According to the precise recipe of Big Bang nucleosynthesis, the universe's first few minutes should have produced a very specific amount of this normal matter. We can calculate that number with confidence, but when we take a census of the modern universe, adding up all the baryons we can actually see locked in stars, glowing in galaxies, and floating as cold gas, we only find about half of what we should. Billions upon billions of solar masses of ordinary atoms have simply vanished from our ledgers. Where could half the universe's normal matter be hiding? It is not in dark matter, which is something else entirely. This is the atoms themselves that have gone missing. The leading suspect is not a hidden vault, but a vast, tenuous, and scorching hot fog that fills the spaces between galaxies. Scientists call it the warm-hot intergalactic medium, or WIM. Picture the cosmic web, that grand structure of filaments and nodes where galaxies cluster. Theorists predicted that the gravitational pull of this web would draw in normal matter over billions of years, heating it to temperatures between 100,000 and 10 million degrees. At these extremes, the gas is so hot it glows not in visible light, but in far ultraviolet and low-energy X-rays. It is also so diffuse that a cubic meter of it might contain only a few atoms, a vacuum far emptier than anything we can create on Earth, yet spread across such colossal volumes that it could account for every single missing baryon. Finding this phantom gas has been a monumental challenge. Its faint signal is easily drowned out by brighter sources, and its preferred wavelengths are largely blocked by Earth's atmosphere. The hunt has required space-based observatories with X-ray vision. Astronomers use a clever trick. They look at the bright light from distant quasars, which act as cosmic flashlights. As this light travels billions of light years to reach us, it passes through the filaments of the cosmic web. Atoms in the WIM, like oxygen and neon heated to millions of degrees, will absorb very specific wavelengths of that quasar's light. By analyzing the quasar's spectrum, scientists can find these telltale absorption lines, thin, dark gaps in the light, and map the presence of the hot gas. It is like finding the silhouette of a nearly invisible fog by watching how it dims a distant street lamp. Piece by piece, the evidence is mounting. Observations from telescopes like XMM Newton and Chandra have begun to detect these absorption features, confirming that the WIM exists and contains heavy elements blasted out from ancient supernova. Other techniques look for a faint, diffuse glow of X-rays emanating from the web itself. The picture emerging is of a universe where normal matter is not primarily in the galaxies we see, but in a shimmering, ultra-hot atmosphere that envelops them, a sea of plasma that is the true reservoir of the cosmos's ordinary atoms. Solving this mystery does more than balance the books. It completes our map of the cosmic ecosystem, showing us where the raw material for future stars and galaxies actually resides, hiding in plain sight in the spaces we once thought were empty. That hot, invisible sea of atoms is the universe's reservoir, but what of the thoughts it might one day hold? While we search for cosmic company, we have already cast our own messages into the interstellar ocean, creating artifacts that may become the deepest enigma of all for anyone who finds them. Attached to the Pioneer 10 and Pioneer 11 spacecraft are small, gold-anodized aluminum plaques. Etched onto them is a cosmic greeting from Earth. There is a diagram of a man and a woman, the man's hand raised in a gesture of goodwill. There is a schematic of our solar system showing the spacecraft's trajectory from the third planet. And most intriguingly, there is a map locating our sun relative to 14 pulsars, the rapidly spinning corpses of dead stars that emit lighthouse-like beams of radio waves. Each pulsar is marked by a line showing its unique spin rate, a kind of galactic longitude and latitude written in the language of physics. The later Voyager probes carried a more ambitious time capsule, the Golden Record. It is a 12-inch gold-plated copper disc containing sounds and images from Earth. There are greetings in 55 languages, the brainwaves of a person in love, the crashing of ocean waves, and music ranging from Bach to Chuck Berry. A stylus and symbolic playing instructions are included on the cover, which also bears the same pulsar map. These are humanity's most deliberate messages in a bottle hurled into the cosmic tides. Yet they contain a profound and unsettling paradox. We have crafted these beautiful, hopeful artifacts with the implicit assumption that intelligence anywhere will share a common framework of logic and perception. But will it? The pulsar map is a masterpiece of scientific universality. Pulsars are natural clocks, their precise spin rates changing in predictable ways over millions of years. An advanced civilization capable of interstellar travel would almost certainly understand neutron star physics and recognize these cosmic landmarks. They could, in theory, trace the lines back to our solar system's neighborhood, even if our sun has grown dim by then. This is the part of the message built on the solid ground of shared physical law. Everything else rests on far shakier ground. Take the simple image of the man and woman on the Pioneer plaque. We see a depiction of two humans, but an intelligence that evolved under a different sky, with a different sensory apparatus and a different evolutionary history, might not perceive a line drawing as a representation at all. It could be interpreted as a single, bizarrely shaped organism, or as a technical schematic of a machine, or simply as decorative patterns with no meaning. The concept of symbolic representation itself may be uniquely human. The Golden Record presents even greater cognitive challenges. The instructions for playing it are pictorial, using simple diagrams to show the record's rotation, the stylus, and the conversion of waveforms into video images. These instructions presume an understanding of technology, of storing information on a physical medium, and of translating time-based signals into sight and sound. A civilization that communicates through chemical exchanges or magnetic field fluctuations might have no cultural context for any of this. The music we included as a celebration of our spirit might be perceived as meaningless noise or worse, as a threat display. The sound of a kiss could be baffling, the image of a supermarket overwhelming. We have sent a snapshot of Earth's biology, culture, and emotion, filtered entirely through a human lens. The terrifying, beautiful possibility is that these records will never be decoded. They may float for eons, pristine and unreadable, their contents an eternal mystery even to a finder with vast intelligence. They become the ultimate locked room puzzle, where the key is a shared experience of reality that may not exist anywhere else in the galaxy. This is the quiet paradox at the heart of our search. In trying to say we are here, we may have only succeeded in creating the universe's most eloquent silence, a monument not to what we know, but to everything we cannot possibly imagine about the mind of the other. Far beyond the realm of the planets, in the perpetual twilight of the outer solar system, lies a ring of frozen relics. This is the Kuiper Belt, a vast disk of icy worlds and debris left over from our system's formation, with Pluto as its most famous resident. For decades, astronomers have mapped this distant frontier, expecting to find a gradual tapering of objects as they ventured farther from the sun's warmth. Instead, they found a wall, at a distance of about 50 astronomical units, roughly where Pluto orbits. The population of Kuiper Belt objects is rich and varied. But just a little farther out, around 50 astronomical units, the number of detectable objects drops off a cliff. It is not a gentle decline. It is a sudden, dramatic edge, as if someone drew a cosmic boundary in the ice and said, "Nothing beyond this point." This sharp cutoff, known as the Kuiper Cliff, is one of the solar system's most puzzling architectural features. Why does this belt of primordial leftovers simply end? One compelling and controversial explanation points to the gravitational hand of an unseen giant. The orbits of some extremely distant Kuiper Belt objects are curiously clustered, as if they are being shepherded by something massive. This is the hypothesized planet 9, a world perhaps 5 to 10 times the mass of Earth, lurking hundreds of astronomical units away on a wildly elongated orbit. Its immense gravity, the theory suggests, could have cleared out the region just beyond the cliff, either ejecting objects entirely or pushing them into orbits that keep them perpetually far from the Sun and our telescopes. The hunt for this phantom planet is ongoing, a modern-day celestial detective story trying to explain a gap in the ice. But Planet 9 is not the only suspect. Another explanation looks back to the solar system's violent youth. In the early days, the giant planets are believed to have migrated, shifting their positions in a gravitational dance that scattered comets and asteroids. Neptune, in particular, is thought to have moved outward from a birthplace closer to the Sun. As it migrated, its gravity could have sculpted the inner edge of the Kuiper Belt, shepherding a vast number of objects into closer, more stable orbits and leaving the region beyond starkly empty. The cliff, then, would be a fossilized record of Neptune's ancient journey, a permanent mark of its gravitational influence. A third, simpler possibility is that the cliff marks the actual outer edge of the original protoplanetary disk, the swirling cloud of gas and dust from which our solar system formed. Perhaps the Sun's birth cloud was simply truncated at that distance, maybe by the gravitational influence of a passing star in our Sun's stellar nursery billions of years ago. In this scenario, there was never much material beyond 50 astronomical units to begin with, so the cliff is not a mystery of removal, but one of original construction. Each explanation paints a different picture of our cosmic neighborhood's history. A distant planet 9 implies our solar system is larger and more dynamically active than we thought. Neptune's migration tells a tale of planetary billiards and chaotic rearrangement. A truncated disk suggests our system's blueprint was shaped by stellar neighbors long since gone. The Kuiper Cliff is more than a curiosity. It is a silent sentinel at the edge of the known, holding within its sharp boundary the unresolved story of how our planetary family was built and what unseen members might still be waiting in the dark. That silent edge in our solar system is a mystery of absence, but at the very heart of our galaxy, astronomers have found a brilliant, unexplained presence. The center of the Milky Way should be a familiar place to us. It houses a supermassive black hole, vast star clusters, and swirling clouds of gas. When the Fermi Gamma Ray Space Telescope turned its gaze there, it expected to see a certain level of high-energy gamma-ray light from known cosmic processes. Instead, it saw a glow that should not exist. There is a massive, diffuse excess of gamma-ray radiation blossoming from the galactic core, extending thousands of light years. It is a mysterious fog of energy with no clear source, a beacon of something unknown happening in our own cosmic backyard. This galactic center excess presents a thrilling puzzle with two radically different solutions. The first possibility is the stuff of Nobel Prizes. It could be the long-sought signature of dark matter itself. According to some theories, dark matter particles are their own antiparticles. When two of them collide in the dense environment of the galactic center, they would annihilate each other in a flash of energy, producing gamma rays as their final signature. The smooth, spherical shape of the excess glow matches what many dark matter models predict. If this is true, then we are not just mapping dark matter's gravity anymore, we are seeing its dying light. It would be the first direct detection of the particles that make up most of the matter in the universe, a discovery that would rewrite physics overnight. The second, more conventional explanation is almost as fascinating. The glow might come from a vast, hidden population of millisecond pulsars. These are neutron stars that have been spun up to incredible speeds, hundreds of rotations per second, by siphoning material from a companion star. They act like cosmic lighthouses, beaming out powerful radiation, including gamma rays. Thousands of these faint, point-like sources, each too dim for Fermi to see individually, could collectively blend together to create the smooth, excess glow we observe. Instead of a dark matter signal, we would be looking at a stellar graveyard, a glittering but unseen metropolis of the dead. Distinguishing between these two possibilities is a cosmic detective story of the highest order. The key clue lies in the texture of the light. A smooth, featureless glow strongly points to dark matter, as the particles would be everywhere, creating a uniform fog. A collection of pulsars, however, would create a speckled glow like seeing the combined light of a distant city at night. From far away, it looks like a uniform haze, but with a powerful enough telescope, you could start to pick out individual streetlights. Astronomers are now using that exact strategy. They are combing through the Fermi data and observations from other telescopes, searching for any sign of pinpoint sources within the excess. Finding even a handful of pulsars there would prove that at least part of the glow is ordinary, though extraordinary, astrophysics. The search is painstaking, like listening for individual instruments within a roaring symphony. This mystery at the heart of our home galaxy is a beautiful example of science at a crossroads. We are faced with two incredible narratives. One reveals the fundamental architecture of reality, the other a hidden stellar population of stunning scale. Both answers are profound. Every new observation, every more sensitive analysis, brings us closer to knowing whether we are seeing the ghosts of the cosmos or the glitter of its ancient remnants. The truth is written in that gamma-ray fog, waiting for us to learn how to read it. That gamma-ray glow from our galactic core is a signature of cosmic processes, but far closer to home. A dying star has painted a masterpiece in the sky that holds a chemical secret. In the constellation Monoceros, about 2,300 light-years away, a sun-like star is in its final throes, casting off its outer layers to form the Red Rectangle Nebula. Through a telescope, it appears as a stunning geometric form, a near-perfect rectangle of glowing red gas with a lattice of dark lanes like cosmic latticework. Its beauty is undeniable, but the true mystery is not in its shape but in its light. When astronomers break that light into a spectrum, they find fingerprints that do not belong to any element or molecule we know. The nebula's light contains two bizarre features. The first is called extended red emission, a broad, unexplained glow in the red part of the spectrum. The second is a series of sharp, unidentified infrared bands, specific wavelengths of light that act like a barcode for a molecule. The problem is, this barcode does not match anything in our terrestrial databases. We have catalogued the spectral signatures of countless compounds found on Earth or created in labs, but the lines from the red rectangle correspond to none of them. This means the nebula is a vast chemical factory producing substances that are entirely alien to our experience. What could these mystery molecules be? The leading suspects are complex carbon-based compounds known as polycyclic aromatic hydrocarbons, or PAH. Think of them as soot on a cosmic scale, not simple specks, but large, flat molecules built from rings of carbon and hydrogen, like tiny, intricate chicken wire. They are robust and could form in the cool, dense outflows from dying stars. Many astronomers believe PAHs are widespread in space and could be responsible for the unidentified infrared bands seen in many nebulae. Yet, even with PAHs, the exact match for the red rectangle's signature remains elusive, suggesting an even more complex or pure form of these carbon structures. There is a more radical possibility. The environment of a protoplanetary nebula is a unique laboratory with intense ultraviolet radiation from the central star bathing the ejected material. This could be forging entirely new forms of carbon-based matter, perhaps even the primordial seeds of more complex organic compounds. Some scientists speculate we might be seeing the spectral signatures of fullerenes, soccer ball-shaped carbon molecules, or even long carbon chains that are the precursors to the building blocks of life. The red rectangle, then, is not just a tomb for a star, but a cradle for novel chemistry. This makes it a critical test case. By studying its light, we are essentially watching chemistry happen under cosmic conditions, low density, extreme radiation, and vast stretches of time that we cannot replicate in any lab on Earth. Each unidentified line in its spectrum is a question. Are we seeing the steps that create the complex organic molecules that might one day seed new planets? Or are we witnessing the formation of an entirely new class of material, a form of matter that exists only in the deep freeze of interstellar space? The red rectangle's haunting geometry frames a profound mystery. What unknown substances are being woven into the fabric of the cosmos right before our eyes? That nebula's alien chemistry is forged in the cold of deep space, but within our own solar system, a different kind of unnatural geometry has held its perfect shape for over 40 years. At Saturn's north pole, a hexagon spins. It is not a trick of shadow or a fleeting arrangement of clouds. It is a six-sided jet stream, a colossal wave of air wider than two Earths combined, tracing a near-perfect geometric path around the planet's pole. When the Voyager probes first glimpsed it in the early 1980s, scientists were stunned. Such straight edges and sharp corners have no place in the turbulent, fluid chaos of a planetary atmosphere. Yet there it was, a honeycomb cell drawn on a planetary scale. The Cassini mission, which orbited Saturn from 2004 to 2017, gave us a breathtaking view of this permanent atmospheric wonder. From high above, the hexagon appears as a pale, six-lobed road encircling a deep, stormy vortex. Cloud speeds within its walls race at over 300 miles per hour. This is not a static shape etched into the clouds, but a high-speed highway of wind, a standing wave pattern fixed in place as the planet rotates beneath it. The question is not just how it formed, but how it has remained so stable, so precise for decades. On Earth, our jet streams meander, buckle, and break. Saturn's hexagon is a monument to atmospheric order. The secret likely lies in the laboratory science of fluid dynamics. If you spin a cylinder of fluid, the outer edges move faster than the center. Under the right conditions, instabilities at the boundary between these different flow speeds can organize into polygons. Scientists have recreated this in labs using water tanks on rotating tables, producing beautiful, fleeting squares, pentagons, and hexagons in the swirling liquid. This suggests Saturn's hexagon is a giant version of this experiment, a wave generated by differences in wind speed at a certain latitude, trapped and stabilized by the planet's deep atmosphere and rapid rotation. But the laboratory analogs are tiny and short-lived. Scaling this up to a planetary phenomenon that lasts for generations is the true marvel. It speaks to the profound depth and strange uniformity of Saturn's atmosphere. The hexagon is not just a skin-deep feature, it is a window into the churning, layered dynamics far below the cloud tops we see. It may be anchored by a deep, planet-wide jet stream, its shape maintained by the energy of internal heat rising from Saturn's core. The stability of the hexagon, compared to the chaotic storms of Jupiter, tells us that Saturn's atmospheric engine, while violent, operates with a hidden regularity. Each sharp corner of the hexagon is a testimony to the precise balance of forces, rotation, wind shear, and thermal gradients, on a world where the very air is a vast alien ocean. This enduring geometric storm is more than a curiosity. It is a natural laboratory for understanding fluid physics at scales we can never replicate, teaching us that even in the riotous atmosphere of a gas giant, the universe can inscribe a shape of perfect, persistent symmetry. That perfect hexagon is a testament to hidden order, but the universe holds a far more pervasive and invisible form of structure, one that threads through the emptiness between stars and galaxies themselves. This is the mystery of cosmic magnetic fields. We tend to think of the void as just that, an empty stage. Yet, space is laced with magnetic fields of astonishing scale. These are not the fierce, localized fields of a magnetar, but vast, subtle webs stretching for tens of thousands of light-years, aligning the thin gas between stars and even bridging the colossal gaps between galaxy clusters. They are the universe's silent, invisible skeleton. Their existence presents a profound chicken and egg problem. How did such coherent, large-scale magnetism arise in what should have been a magnetically neutral cosmos? The fields we see today are too widespread and too organized to have simply grown from scratch after galaxies formed. It would be like trying to create the Earth's entire weather system from a single, gentle breeze. The process would be far too slow. This means these fields must have incredibly ancient origins, seeds planted in the universe's infancy that were then stretched and amplified by the motions of gas and stars over billions of years. But what planted those seeds? One compelling theory takes us back to the universe's first moments. In the searing heat of the Big Bang, as the cosmos expanded and cooled, it may have undergone dramatic phase transitions, similar to water freezing into ice. These shifts in the state of the fundamental forces could have generated tiny, random magnetic fields everywhere at once, a primordial fuzz of magnetism woven into the fabric of spacetime. These weak seeds would then have been caught up in the first swirling motions of gas, stretched and twisted by gravity as galaxies condensed, growing stronger and more organized over cosmic time. Another possibility points to the first generation of stars and black holes. The earliest stars were behemoths living fast and dying in colossal supernovae. Their violent deaths and the frenetic activity around the first supermassive black holes could have acted like cosmic dynamos, generating powerful magnetic winds that blew out into the pristine intergalactic medium. This would be a more localized seeding process, with magnetism spreading like ink in water, eventually merging to form the large-scale fields we detect. The true answer likely involves both a whisper from the primordial universe, later shouted into coherence by the first structures. Understanding these ghostly fields is not just an academic exercise. They are fundamental actors in the cosmic drama. They guide the collapse of gas clouds to form new stars, providing a subtle pressure that can slow or shape the birth of solar systems. They are the highways and traps for cosmic rays, those ultra-high-energy particles, bending their paths and confining them within galaxies. They shape the very structure of the interstellar medium, the thin soup of gas and dust between stars, organizing it into filaments and bubbles. We detect these fields indirectly by observing the subtle polarization of starlight as it passes through magnetically aligned dust grains, or by measuring the radio emission from electrons spiraling along magnetic field lines. Each observation is a clue to a story that began before the first star ignited. Solving the mystery of cosmic magnetism is about tracing a thread from the first microseconds of reality to the swirling clouds where planets are born today. It is a search for the signature of creation's first currents, written in the silent force that guides the galaxy. The silent, magnetic threads that bind the cosmos are just one of the many frontiers where our understanding ends and wonder begins. From the phantom push of dark energy to the perfect hexagon at Saturn's pole, these 25 mysteries are not merely gaps in a textbook. They are the very edges of the map, the places where the known universe dissolves into questions. Each one, from the missing lithium in the stars to the ghostly halo of dark matter, represents a fundamental challenge to our perception of reality. They remind us that the cosmos is not a solved puzzle, but a living, breathing riddle, constantly revealing new layers of complexity the closer we look. This journey through the unknown highlights a humbling and beautiful truth. The more we discover, the more we realize we do not know. Every answered question seems to unlock 10 more, each more profound than the last. This is not a failure of science, but its greatest triumph. It is the engine of curiosity, the force that has propelled us from gazing at campfires to mapping the afterglow of creation itself. And right now, we stand on the brink of a new age of discovery. Instruments like the James Webb Space Telescope are peering into the atmospheres of distant worlds and the nurseries of the first galaxies, seeking clues to our origins. The Vera C. Rubin Observatory will soon begin its relentless scan of the sky, catching the fleeting dance of interstellar visitors and the subtle warping of dark matter. These missions are our new eyes on the cosmos, built to probe the very enigmas we have explored. They are humanity's collective effort to push the boundaries of the known, to turn these mysteries into understanding. So let this not be an end, but an invitation. Stay curious, look up at the night sky, and remember that every point of light holds a story we are still learning to read. The greatest chapters of our cosmic story have yet to be written, and you are here to witness them unfold. We want to hear from you. Of all these 25 cosmic mysteries, which one captivates your imagination the most? Is it the terrifying silence of the Fermi paradox, the bizarre shadow of Tabby's star, or the phantom planet that might sculpt our solar system's edge? Share your thoughts in the comments below, and if you are hungry for more journeys to the edge of understanding, subscribe and join us as we continue to explore the deepest wonders of space.